Hello, chemistry students, and welcome to the Organic Chemistry Laboratory. Today we will be performing our introduction to the microscale laboratory experiment. In this experiment, we will introduce some of the equipment and show how to assemble some of the apparatus that will be needed for further experimentation. A more detailed look at some of these methods can be found in the techniques section of your laboratory textbook. Let's get started. One of the more common pieces of glassware in the microscale laboratory is a conical reaction vial. This is a 5 milliliter conical reaction vial. And we'll often use these vials to store our chemicals. And in order to do this properly, we need to use an insert and a cap. Now this insert has two sides. This white side is a Teflon material, and the opposite side is a silicone rubber material. And we need to store our chemicals so that the Teflon side of the insert is facing inward towards the chemical. To do this, you'll just insert the insert into the cap so that the Teflon side is facing down, and then we can just screw the cap and the insert onto the top of the conical reaction vial. And this is how we properly store chemicals in our conical reaction vial. Now we can also use these caps along with O-rings. So we have our cap here and an O-ring here to assemble more complex apparatus. So today we'll be assembling a reflux apparatus as an example. And to do this, we have our air condenser here. And so we'll take our cap and slide it over the glass joint at the bottom of the condenser. And then we'll place an O-ring over that same glass joint. We can then screw the cap and the condenser onto our reaction vial. This is our fully assembled reflux apparatus. So we have a hot plate with an aluminum block on top of the hot plate, and our aluminum block has a hole where we can insert a thermometer and record the temperature of our aluminum block. We've also inserted our conical vial into another hole in our aluminum block, and our conical vial is secured to our air condenser using our cap and O-ring. And we secured our whole reflux apparatus to a ring stand using a utility clamp. And we've inserted a thermometer down into our reflux apparatus so that we can record the temperature of our refluxing vapor. In this part of the experiment, we're going to use sodium chloride salt and a micro spatula to weigh out approximately 1, 0.5, 0.1, and 0.01 grams of sodium chloride salt. So you first want to always make sure that you're either using weigh paper or a weigh boat when measuring something out on a balance. This is our mass for attempting to weigh out approximately 1 gram of salt. Our mass is 1.0005 grams of sodium chloride salt. This is our mass when attempting to weigh 0.5 grams of sodium chloride salt. The mass of our sodium chloride salt is 0.5007 grams. This is the mass when attempting to weigh 0.1 grams of sodium chloride salt. The mass of our sodium chloride salt is 0.1004 grams. This is the mass of our sodium chloride salt when attempting to weigh 0.01 grams of sodium chloride. The mass of our sodium chloride salt is 0.0103 grams. For part A of laboratory exercise 1 of this experiment, we're going to determine the density of water and hexane using an automatic micropipette and a 3 milliliter conical vial. So we first need to determine the weight of our 3 milliliter conical vial, our Teflon insert, and our cap. The mass of our 3 milliliter conical vial, cap, and Teflon insert is 18.2818 grams. We next need to transfer 0.5 milliliters or 500 microliters of deionized water, and this is our deionized water, to our 3 milliliter conical vial using an automatic micropipette. Now this automatic micropipette is accurate between 100 and 1,000 microliters. And we determine the volume that we are transferring using the micropipette using these three numbers on the side. Now this top number in red represents the 1,000s place for microliters. The middle number is the hundreds place, and the bottom number is the tens place. So right now this is showing that we'll have 500 microliters if we use this to transfer any volume of liquid. Now to use this micropipette, we need to press the plunger down to the first stop and then slowly draw the plunger back up while our tip is inside the liquid. And then to dispense it, we will press the plunger all the way down to the first stop and then also down to the second stop to make sure that all of the liquid is expelled. Now we first need to attach a disposable tip to our automatic micropipette. We'll then insert our tip into the deionized water and slowly draw the plunger up. We'll then remove the tip and transfer the deionized water to our 3 milliliter conical vial by pressing the plunger down all the way to the first stop and then down to the second stop and removing the tip before we draw the plunger back up. We'll now determine the mass of our conical vial cap and insert along with our 500 microliters of deionized water. The mass of our conical vial plus the 500 microliters of deionized water is 18.7833 grams. We're now going to repeat the procedure using hexane. So we first need to determine the mass of our 3 milliliter conical vial, cap, and Teflon insert. The mass of our 3 milliliter conical vial, cap, and Teflon insert is 22.5663 grams. We're next going to use our automatic micropipette to transfer 0.5 milliliters or 500 microliters of hexane to our 3 milliliter conical vial. So we need to place a disposable tip on our automatic micropipette, press our plunger down to the first stop, insert our tip into the hexane, and slowly draw up our plunger. And then we'll transfer our hexane by pressing down to the first stop and then all the way down to the second stop. We'll then cap our conical vial containing the hexane and always make sure that the Teflon part of your insert is facing down towards your chemical. We'll now determine the mass of our conical vial and the hexane. The mass of our conical vial and the hexane is 22.8856 grams. You should now be able to determine the densities of water and hexane. We'll next determine the densities of water and hexane using a graduated pipette. So we first need to record the mass of our conical vial that we will be using. The mass of the conical vial that we will be using to determine the density of water is 18.2881 grams. We'll now use our graduated pipette to transfer 0.5 milliliters of deionized water to our 3 milliliter conical vial. And we'll determine the mass of the water plus our conical vial. The mass of our conical vial plus the 0.5 milliliters that we transferred using the graduated pipette is 18.7948 grams. We now need to determine the mass of the conical vial that we will be using to determine the density of hexane using a graduated pipette. The mass of our conical vial is 22.5666 grams. We'll next transfer 0.5 milliliters or 500 microliters of our hexane to our 3 milliliter conical vial using a graduated pipette. And then we'll determine the mass of our hexane plus the conical vial. The mass of our conical vial plus the hexane that we transferred using the graduated pipette is 22.8988 grams. You should now be able to determine the densities of water and hexane from our transfers using the graduated pipette. We're next going to determine the densities of water and hexane using a disposable Pasteur pipette to transfer the volumes of water and hexane. So we first need to determine the mass of our conical vial for the water. The mass of our conical vial is 18.2917 grams. We'll now transfer 0.5 milliliters or 500 microliters of our deionized water to our conical vial using our disposable Pasteur pipette. And we'll determine the mass of our conical vial plus the deionized water. The mass of our conical vial plus the water using the Pasteur pipette is 18.7831 grams. We next need to determine the mass of the conical vial that we'll be using to determine the density of hexane using a disposable Pasteur pipette. The mass of our conical vial for the hexane is 22.5666 grams. We'll next transfer 0.5 milliliters or 500 microliters of hexane to our conical vial using a disposable Pasteur pipette. And we'll determine the mass of our conical vial plus the hexane. The mass of our conical vial plus the hexane using the disposable Pasteur pipette is 22.8423 grams. You should now be able to determine the densities of water and hexane from our volume transfers using the disposable Pasteur pipette. For laboratory exercise 2 of this experiment, we're going to calibrate a glass Pasteur pipette. And to begin to do this, we first need to weigh out approximately 0.5 grams of deionized water, which I've already done in this conical vial. And in another conical vial, weigh out approximately 1.0 grams, which I've done in this conical vial. We're then going to attach our Pasteur pipette bulb to the end of our glass Pasteur pipette. And we'll draw up the 0.5 milliliters of deionized water completely into the glass Pasteur pipette.
And once we have all of it, we will mark our glass pasture pipette with a pen where the 0.5 milliliters filled up the pasture pipette to, and then we will repeat the same procedure using the 1 milliliter volume of deionized water. We can then return the water back to the conical vial. We can remove the pipette bulb, and we'll use a metal file to score where the 1 milliliter and the 0.5 milliliter marks were on our pasture pipette. And you should now be able to see where we've scored our pipette and calibrated. So this is our 0.5 milliliter mark on our glass pasture pipette, and this is our 1 milliliter mark on our glass pasture pipette. And that's how we calibrate a glass pasture pipette. You can now calibrate additional glass pasture pipettes by placing them next to the original one you calibrated and then scoring the additional pasture pipette at the same mark that you had previously scored on the one that's already been calibrated. In the next part of this experiment, we're going to demonstrate the technique used in performing an extraction. Extractions are important in organic chemistry because they allow us to separate organic reaction products. So what we need to do first is we're going to take a conical vial and we're going to add 1 milliliter of deionized water. And we're also going to add 1 milliliter of hexane. And we'll cap our conical vial, and you should be able to see that we have 2 immiscible layers of solvent inside our conical vial. And so when performing an extraction, we'll shake the vial, and this will allow our reaction product solutes to migrate into whichever layer, either the organic or the aqueous, we are using to extract our product solutes. So you can see again that we have our 2 immiscible layers inside of our conical vial. Now in this case, because water is more dense, the aqueous layer is on the bottom and the organic layer, or a hexane, is on the top. And what we're going to do next is we're going to remove the cap from our conical vial containing our aqueous and organic solvents, and we're going to separate our 2 solvents by inserting a glass pasture pipette with a pipette bulb so that the tip of the glass pipette goes all the way down to the bottom of our conical vial. And we're going to draw up the bottom layer, or in this case, the aqueous layer, from our conical vial into our glass pasture pipette, and we're going to leave our organic layer, or in this case, the hexane layer, down in our conical vial. So we'll insert our pipette down to the bottom of the conical vial, and we'll draw up our aqueous layer, and we'll transfer that layer into our new conical vial. And this is how we perform an extraction. We now have just the aqueous layer in this conical vial. You can see there's no longer 2 immiscible solvents in the conical vial. And we only have our organic layer, or hexane, remaining in the original conical vial. You can see there's no more aqueous layer down in the bottom of the conical vial. And this is the technique we use to perform extractions.
This concludes our introduction to the microscale laboratory experiment. Thank you for joining me for this laboratory.